Hello, and welcome back to the course on Physics for Engineers. So we are now on the second to the last lesson for this chapter on electromagnetism. So let us first review some concepts. So we have discussed about Faraday's law in the previous lesson, which is just the negative time rate of change of the magnetic flux. And for this lesson, we will be talking about inductance and introduce another circuit element called an inductor. So before we introduce what is an inductance and an inductor, let's first discuss the concept of mutual inductance. So if you have a coil, say two coils, one coil can actually induce an EMF on another coil, and that other coil can actually also induce an EMF on the other coil if both of these coils have changing current or changing magnetic flux. And this is what we call mutual inductance. They have mutually induced EMFs on each other, and we say that these two coils are now coupled. So mutual inductance basically describes the coupling between two coils. So a coil can induce a current on the other coil and vice versa. So these are the mutually induced EMFs, and it's due to the changing current. So the EMF induced on coil number 2 is due to the changing current in coil number 1, and similar with the induced EMF in coil number 1, which is due to the changing current in coil number 2. And the term M here is what we call the mutual inductance, which depends on the number of turns the flux on coil number 2 over the current on coil number 1. And similarly, you can also formulate it in this manner. So the standard unit for inductance, whether it's mutual inductance or basically just inductance, is the unit called Henry. And 1 Henry is equal to 1 Weber per ampere, or 1 volt per second over ampere, or 1 ohm second. So these are the unit equivalent for Henry, the inductance, standard unit for inductance. So there are actually many applications of mutual inductance. So for example, wireless charging, whether you are wirelessly charging your toothbrush, or you are wirelessly charging your cell phone or your smartphone, or you are cooking using an induction cooker. So an induction cooker uses a special type of frying pan which has coils in it, so there will be an induced current on the coil. So in this example here, at the bottom of this toothbrush, there's actually a coil, and at the base of this charger is actually another coil. And these two coils mutually induce EMF on each other. And that is how wireless charging works. You need two coils. Okay. So another example or material which uses or a device which uses mutual inductance is the transformer. So it basically operates based on mutual inductance. So you have two coils, the primary coil and the secondary coil, and they are wound in a single core. So the core is metallic, and since it's metallic, the magnetic field is actually just confined within the core. So meaning changes in magnetic field is actually just within this core here. Now, the primary coil can have different number of turns, voltage, and current, similar with the secondary coil, and power is actually the same between the two coils. So the relationship between the number of turns and the current is actually inversely proportional. So the higher the number of current, the higher the number of turns of the coil, the lower the current, and the lower the number of turns, the higher the current. And similarly for voltage, it's directly proportional. So the higher the voltage, the higher the number of turns, the higher the voltage. The lower the number of turns, the lower the voltage. And power is conserved in a transformer. So if you will recall, power is voltage times current. So meaning, in terms of power, voltage and current is inversely proportional to each other. So the larger the voltage, the lower the current, and the lower the voltage, the larger the current. So from here, we see that in this example, specific example, you have a small number of turns here. So if you have small number of turns, meaning you have large current. But if you have small number of turns, meaning you also have a small voltage. So basically, small number of turns, small voltage, large current. Large number of turns, large voltage, small current. Okay. So one advantage of transformers is they can step up and step down the voltage. So if you want to convert your voltage to a higher or lower one, you need a transformer. So we actually see transformers every day. When you go out in the street, you see posts like this, maybe just in the Philippines, you see posts like this, and these things here are the transformers. So these are actually step-down transformers. So the power from our electricity providers are actually high voltage, low current. And when it comes to our household, it is transformed by this transformer to a lower voltage, 220 volts, and larger current, 10 amperes. So it's a step down. The things that you see here in the Philippines, these are step down transformers. Okay, so let's now introduce inductance and inductors. So inductance or self-inductance is basically just the induction effect by any coil on itself due to the variation in its own magnetic field. So if you have two coils, there's mutual inductance. But if you just have a single coil, and that coil has a changing current, therefore it has changing magnetic field, and therefore it has a changing flux, then therefore it will have an induced EMF on its own, on itself. And that's basically a self-inductance or plainly inductance. So a coil can induce an EMF on itself, especially if the current is changing. So if the current is changing, the magnetic field is also changing, therefore the magnetic flux is also changing. So change in magnetic flux, induced EMF. So this is the inductance. It's just related to the number of turns in the coil, the flux through the coil, and the current. So the self-induced EMF will just be related to the inductance time, the change in current with time. So an inductor, similar to a capacitor or a resistor, is just a device with a specific inductance, or specifically a coil with a specific inductance. Sometimes you also call this a choke or the magnetic balance. Examples of this are the magnetic balance and the spark plug. So in your motorcycles or in your vehicles, you actually have a choke. If you find your vehicle to be hard to start the vehicle, you actually choke the vehicle. So that's actually the spark plug. The spark plug in your vehicle that's actually an inductor. So this is the circuit symbol for your inductor. It's basically just a coil. So magnetic ballast in fluorescent light tubes. I don't know if you're familiar with this, but since most of our lighting technology now is LED, but the old fluorescent light tubes uses magnetic ballast. It's the purpose of that is to control the surge or the increase or decrease in current. So similarly, our transmission, electrical or power transmission systems have inductors. The brown spirally things that you see on top of the wires, these are inductors. So if lightning strikes an electrical power system or a wire, it will cause a sudden spike in current, an increase in current. So if you have an inductor, the increase in current will be counteracted by the induced EMF in the inductor. So it will protect, an inductor will protect the power grid or the power system. So that's the purpose of an inductor, to control, to counteract the effect of increasing or decreasing current. So it will induce a magnetic field, it will induce an EMF, it will induce a back EMF or a back induced current. Okay. So let's compare it with the resistor. If there's a resistor and there's a constant current flowing from point A to point B of this resistor, there will be a voltage drop in this resistor. So there will be power drop, power will be dissipated in the resistor, and there will be a voltage drop. And the voltage drop is equal to I times R. So if you have a current, a constant current flowing through an inductor, there will actually be no voltage drop if the current is constant. Because again, there's only a back EMF, an induced EMF or induced current, if there is a change in a current or change in magnetic field or change in flux. But if for a constant current, it will have a constant magnetic field, it will have a constant flux. So if the current is increasing, there will be a back EMF in the opposite direction. If the current is decreasing, then there will be a back EMF to support the decrease in current in the same direction. So that is the purpose of an inductor, to control, to as much as possible make the current not change in a circuit. So to maintain the current constant in a circuit. That's the purpose of the inductor. So it's basically a regulator, a current regulator. Now, similar to a capacitor stores electric potential energy or electric field energy. So the energy actually, electric potential energy is actually stored within the electric field if you have a capacitor. In the same manner, magnetic potential energy is actually stored within the magnetic field of an inductor. So the magnetic potential energy U maximum is actually 1/2 Li squared. L is the inductance, I is the maximum current in your system. So if you have a resistor and current is flowing through your resistor, energy is actually dissipated. Dissipated means lost. Energy is lost. Energy is given to the resistor. Energy is given by the current to the resistor. Now, if you have an inductor and the current is changing through the inductor, energy is actually stored or released. So energy is stored when the current is increasing. So when there's an increase in current, meaning there's a surplus in energy, surplus in magnetic field energy. And that surplus, that extra energy, is actually stored within the magnetic field in the inductor. Now, during the time when the current is decreasing, then the current is released, or the energy is released. Energy is released by the inductor to support the decreasing current. So that's the good thing about an inductor. It's a regulator. So if there's an increasing current, it will store the extra energy. If there is a decreasing current, it will release energy so that as much as possible, the current flowing in the system is constant. So the energy required to fire an automobile spark plug is actually derived from the magnetic energy, field energy, stored in the ignition coil of your vehicle. Okay, let's have an example. So this is for a transformer. So sorry, I made an error. This is a step-down transformer. So you bought an appliance from Japan, which has a power or voltage rating of 100 volts, and wants to use it in the Philippines, where the voltage rating is 220 volts. So what should be the ratio between the number of coils N1/N2 of the transformer that you need? And what is the output current of the transformer if the current rating of the appliance is 2 amperes? So this is a Japanese, you have a Japanese appliance, and you want to use it in the Philippines. So meaning you have to, if you're using it in the Philippines, you need a step-down transformer. Since the Philippines has a 220 volts voltage rating, you need to step down the voltage to 100 volts. And you need these types of transformer. So you need to plug it in to a 20 volt source, and it will give you an output of 100. Okay. So the ratio is just N1/N2, and that's basically just the ratio of the voltage, V1/V2. So V1, the input, is 220 volts. V2, the output, the secondary coil, is 100 volts. Therefore, the ratio should be 2.2. Okay. So what is the output current of the transformer if the current rating of the appliance is 2 amperes? So knowing the number of turns, or the ratio of N1 over N2, so I2, the output current is just the ratio N1 over N2 times the input current I1. Okay, so the current input rating of this appliance is 2 amperes. So meaning times 2.2, this will give you 4.4 amperes. So step down transformer, it steps down the voltage from 220 to 100 volts, and therefore it increases the current from 2 amperes to 4.4 amperes. Okay. So step-up transformers increase the voltage while decreasing the current, and the reverse, actually the reverse of the step-up transformer, step-down transformer, they decrease the voltage. So in this case, from 220 volts, they decrease it to 100 volts, and they increase the current from 2 amperes to 4.4 amperes. Okay, let's have another example. So this is how to store energy in an inductor. So I have presented to you this example earlier. So the electric power industry would like to find efficient ways to store surplus or extra energy generated during low demand hours to help meet customer requirements during high demand hours. So perhaps a large inductor can be used. So what inductance would be needed to store 1 kilowatt hour of energy in a coil carrying a maximum of 200 ampere current? So we know the energy. The energy is 1 kilowatt hour. We know the current, 200 ampere. So we just need to find the inductance, L. So 1 kilowatt hour, that's actually 3.6 times 10 to the 6 joules. So knowing the, using this equation for magnetic field energy stored in an inductor, 1/2 Li squared, solve for L, 2U over I squared. So convert the energy from kilowatt hour to joules. Then this is the current, and you will get 180 Henry. So this is the inductor needed so that the extra energy generated by the electric power industry during low demand hours, say low demand hours, so what time is that? During night time. The extra energy will be stored in these inductors, and it will be released during the high demand hours when the current is very low. So the low demand hours current is very high because only a few people are using, or a few households are using electricity. So at high demand hours, since more people are now using, more households are now using, so the current will decrease, and this will cause the inductor to release some of its energy to counteract the decreasing current. And that is the end of this lesson. So for the last lesson, we will basically just be generalizing this chapter, and we will discuss the collection of equations called Maxwell's equation. So I will see you again on the last lesson for this chapter.